Hello, I'm Amco and this is Corrected Below. In this video, we will take a look at the absolute basics of TensorFlow and build a small neural network that can learn the XOR function. First of all, we import sys and TensorFlow. Then we print the version of Python and the version of TensorFlow. Now we know TensorFlow is correctly installed, and if you have trouble following this tutorial, you can easily see whether you're using the same version as I do. Sometimes new versions break backward compatibility. Now let's start with a constant. And then print it. Now we see that we have a constant tensor of the float32 type, which is the default. Let's add a second constant, and then multiply them, and print the result. And what do we get? A tensor of the type multiplication. So we don't get the result, we just get a tensor with the graph that does the multiplication. To evaluate the graph, we need to create a TensorFlow session. We can now run a graph in the session and output the value of our first constant. When we run it, we see the value of the constant instead of the tensor itself. We can also evaluate multiple graphs in a single call. We get a list of all the results at once. 3, 7, and for the multiplication, 21. Very often we want to get multiple results at once. For example, you want to train a network and get the loss at the same time. Next up, let's remove these annoying warnings. I use the binary distribution of TensorFlow and it's not optimized for my CPU. To hide the warnings, we need to set the TensorFlow log level environment variable to 2 or higher. Level 1 would only hide the GPU info, but not the warnings. Note that this needs to be done before the session is created. And since it cannot be done too early, I'll just put it up here. You could also define it as environment variable already before you run the script. Working with only constants would get boring quite quickly. So let's introduce variables. Variables are, just like in any other programming language, values that can be updated. Let's do something a bit more neural network-like, and create a single variable for a weight and one for a bias. These are good candidates for variables because they should be updated during training. Seems simple enough. But when we try to run it, bang, doesn't work. Near the end you can find attempting to use uninitialized value. Just giving a variable a default value doesn't initialize them. So let's initialize the variables. Yes, it's that simple. Just make sure it's the last thing you do before you run the graph and you should be good. Let's see what we get now. Yeah, it works. In addition to constants and variables, there are placeholders. Placeholders are used as input values for the graph. Now we have a placeholder, we can feed it into the graph. The simplest graph we can feed it into is the tensor itself. Isn't that amazing? We can get the same value out as we put in. Try that without TensorFlow. Let's calculate something slightly more interesting. Something more like what we would need for a neural network. And now print the result of this. Looks good. Let's now extend this simple network to have two inputs. More accurately, we still have one input tensor, but it's now a 2D tensor with two values. You can ignore the outer dimension for now and consider it a single list with two values. With two input values, we also need two weights. The placeholder does not need to be updated since we did not define the shape. Now we run this, we get our answer in a list. There's just one value in the list and we ignore that it's a list for now. Let's add a second layer since we already have a functioning neural network. Well, sort of. By creating two biases in our first layer, we'll end up with two hidden nodes. Let's also change the values in the second layer. And last thing left is to hook up the two layers. Since this is not the output layer, we apply an activation function. Here I will use the sigmoid for no good reason. This value is then fed into the output layer. The only difference here is that we normally don't use an activation function on the output layer. And this is all there's to it. We now have two layers. It's nothing very useful, but it works. That was pretty straightforward, but a fairly low-level approach. TensorFlow also has higher level APIs. Today we'll use one called layers to do exactly the same thing. First change is that we need to define the shape of the input placeholder. This wasn't necessary earlier, but layers will use this information. Our input consists of two values and it comes in a list of arbitrary many input pairs. This is again the one dimension we ignored earlier. This dimension is used to process batches of values at once, but for now we'll stick with a single value. TF layers dense creates a fully connected network, just like we did before. We first create a hidden layer with two input nodes and then the output layer with one output. Since we use X as the input for the hidden layer and the hidden layer as input for the output layer, TensorFlow knows exactly how to hook these things up. For the activation function, you can simply pass whatever function you want to use, or leave it out if you don't want to use an activation function, like with the output. If you want a deeper network, just rinse and repeat. However, we did get another value now. That's because we didn't assign values to the weights and biases. By default, they get a random assignment. Although it's not very useful, you could provide the initial values for the weights and biases. Note that the shape of the variable in the constant initializer doesn't matter. And with this we get the same result as before, except for some rounding errors. We now have a neural network that can take two values and output one result. Let's see how well this works as an XOR function. Nothing changed in how we run the input through the graph, except we now just provide a batch of 4 input pairs at once. Now we have 4 results, one for each input pair. And clearly they're pretty bad, they should be 0, 1, 1 and 0. Let's calculate the error starting by subtracting the expected result from the output. As expected, all values are pretty far off. Now to turn it into a single number, we could just take the mean. And that doesn't look half bad, which doesn't make sense because we know it is very bad. The problem is that some values are too low and others too high, so on average they seem quite okay. We can get all errors to be positive by squaring them. Now all error values are positive, we can try to take the mean again. Now we can take the mean of the squared errors to get a single number again. It's still just a single number, that doesn't say all that much, but it's a lot more than the 0.05 we had earlier. Let's now move the loss function to TensorFlow so it can be calculated on the GPU. As inputs, we use the same inputs as we already use to calculate the predictions. The other input should be the expected outputs, the answers, so we can calculate the loss. To be able to input the expected answers, we need a new placeholder. The shape of the answers could simply be a list of floats. Just like for the inputs, we do not need to specify how many values we pass in one batch. The graph to calculate the mean square error is pretty simple. TensorFlow has a function to take the square and one to reduce the list of results to a single mean value. Note that we use the y here as predicted value. This is the complete graph and calculates the predictions based on the inputs x. Now we have the same answer except of some rounding errors. Now we know how bad the current weights are, let's learn better ones. First we create an optimizer, and since the Adam optimizer is usually a good pick, we'll take that. A learning rate of 0.01 is a common initial guess. Next we define training as using our optimizer to minimize the error. Beware that the Adam optimizer creates some internal variables. Those variables need to be initialized too, so make sure to call the initializer after you have created the optimizer. The only thing left to do now is actually train. The result after backpropagating once is a little better, after twice again a little better. Now we can repeat it a couple more times. And see, it's not always getting better. To see whether this actually works, we need to train many more times. For example, we could try training about 2000 times. Since the error fluctuates a bit, we only display it after every 250 times training. Now we see the error actually decreases. Success! Let's see what values are output for each input. There we have it! It actually works! Who would have thought that? One thing we can still clean up is the initialization. For this tutorial it was nice to have something you can copy and expect identical results. However, normally you would initialize your weights randomly. Finally, if you would like consistent results between runs, you could set a random seed. This will make sure the same pseudo-random numbers are generated each time you run the script. Now we get the same results every time we run. Seems like we're lucky with this completely randomly chosen seed, as it converges in less than 2000 rounds. In this video we went through the absolute basics of TensorFlow. We saw that in TensorFlow you first build a graph and later run your data through that graph. Using the higher level layers API we can build a neural network in just a few lines of code. Then a couple more lines to define our loss function and finally the optimizer to minimize the error. This is all we need to learn the XOR function, because TensorFlow handles all the difficult math such as calculating derivatives for backpropagation behind the scenes. Thanks for watching. Please like, subscribe and leave your corrections below. Bye!